Welcome back. In this lecture, we will discuss fairness criteria. So let's say you have your machine learning model, you've trained it, you've validated it, you've tested it, it's all ready to go. What other things should you be thinking about? Well, in this course we spoke a lot about bias, and in this module we are looking at fairness. And understanding fairness criteria gives you some potential measurements that you can use to gauge how fair your machine learning system is. In a different lecture, we will also look at some available software that can help you do this more easily. But for now, we're going to focus on the criteria in this particular lecture. So here's our objective. We're going to look at fairness for individual, group, and subgroup. And so it's divided up into these three categories. So let's start with individual fairness, and that is when a system provides similar results for similar individuals, regardless of, say, protected attributes like age, race, and so on. And so some common interpretations of this. So first is fairness through awareness, and that is if you look at two individuals that have similar attributes, even if they have different protected attributes. So when we talk about similar attributes, we mean, in terms of non-protected items. They should be close together in the feature space. So if you have two individuals of different races, but all the other kind of factors that we're evaluating on in the machine learning model are very similar, they should be close together in the feature space. It shouldn't end up being, very far apart. And one way to do this is through distance measurements. And we have had previous lectures where we looked at distance measurements. The next is called fairness through unawareness. And this is simply ensuring that protected attributes are explicitly not being used in the decision-making process. And a third one is counterfactual fairness. And this is where an individual is treated in the same fashion by the system, even if that individual is suddenly placed in a different group, whether it's like racial or ethnic or other groupings based on protected attributes. And so the idea here is you could actually look at the feature vector for an individual and then modify it as needed so they are, the demographic information is driving them to be in a different group, and then the machine learning model should provide similar results. So next is looking at group fairness, and this is when the system treats different groups equally. So here are some common interpretations. So first is demographic parity, and that is when the likelihood of a positive outcome is the same regardless of if the individual is in a protected group or not. One thing to note about group fairness, since now you're looking at evaluations with populations of individuals, so you have many samples, this is a great way to tease out if the system is doing any kind of indirect discrimination. And so it might be difficult to, take the individual approach if you have taken a lot of care to rule out any explicit attributes, but you might have some indirect attribute that is closely correlated with a protected attribute lurking in your data. So a good way to do that is see if you have in your data set, you've identified people from a certain, ethnic, gender, age group, and then just do the test and see, hey, we have these two different groups, and are the results for the model looking very similar. Next is conditional statistical parity, and that is if you have individuals in both a protected and non-protected group they have the probability of being assigned the same positive outcome conditioned on the same set of legitimate attributes. So kind of going along the lines of looking at individuals that are very close with a set of features despite being in different groups. Now we're looking at different groups, and but the measurement here is based on assigned a positive outcome. And so this is when your machine learning model is used to make a decision on something like, hey, this individual is at a low risk for being rearrested, or this individual is very creditworthy. Those are examples of positive outcomes, positive labels that the system would assign. So equalized odds is similar, except now we're measuring true positives and false positives. So it's generalized a little bit further. Equal opportunity is now you're looking at the protected and unprotected groups having equal rates for true positives. Treatment equality, this is looking at the ratio of false negatives to false positives between the groups. So as you see, for each of these four, we're comparing different groups, but we're looking at different measurements. Test fairness. Here is the probability of an individual in a group belonging to the positive class will be the same across all groups. So you could think of this as kind of meta-analysis moving beyond your typical measurements associated with evaluation. So then the third type is subgroup fairness. And subgroup fairness, the idea here is we're trying to have the best of both worlds. And so this can leverage some of the ideas from both individual and group fairness. And the intuition is select a fairness constraint and whether it holds over a large collection of subgroups. So you have all these subgroups within a group, and then any definition from either individual or group fairness, you see if there is parity across the subgroups. So some notes on all these measurements. So first is that you're not going to meet all these criteria simultaneously. There's been research to show that it's very difficult to ensure that you could meet everything at once. And there's like statistical and mathematical reasons for this. Understanding the impact of these measurements over time is also key. So looking at a snapshot may not be true over a longer period of time, and also enacting measures to ensure fairness could have effects that may in the future lead to the algorithm actually becoming unfair. Also, measurement errors can, of course, skew these results. Of course, when you're looking at numbers like true positives and false positives, this is based on a test set, which is just a sample of the population. So if you have some kind of skew in your test set, then you're also going to have errors in your fairness results as well. So it's very important to make sure that, say, your test set is maintaining appropriate statistical properties. And regardless of whatever you use to measure this, so all of these things we talked about in this lecture are really to give you a hint that there is some sort of discrimination or bias in the system, and to point you to that so you can try to eliminate that bias or discrimination. And that's really the point of these measurements. It's not to give you a get-out-of-jail-free card if someone comes to you later and saying, oh, that algorithm's unfair, and you're like, well, I did all these tests. That's not the point here. The point is to try to eliminate the source of the bias. So in designing a system, you have to consider what are the likely sources of bias. If it's a supervised model, where are you getting that data that you're training everything on? Are you taking a close look at that data? And are you understanding that is there a potential bias in the data that is now propagating through the rest of the system? And these measurements we talked about in this lecture are just to kind of give you a window into that. But at the end of the day, we see there's some issues here that, could be challenging. You have to understand where the bias could be coming from and be able to attack that part of the problem. So anyway, this concludes our lecture on fairness criteria. Stay tuned for more content.